Welcome back to the deep dive. Today, we are opening up the hood of the internet.
Hmm.
We all spend our lives scrolling, buying things with one click, streaming video on a bus. It just feels so seamless.
It feels automatic.
But the engineering required to make that happen, especially when you have millions of people doing it at the exact same second, it's basically a modern miracle.
It really is. It's the difference between, say, building a log cabin
Yep.
and building a city that houses 10 million people.
Right.
And that city never sleeps, and it has to withstand earthquakes and floods without anyone even noticing a crack in the pavement.
That is the perfect analogy. So, to guide us, we're
Mhm.
digging into Chapter 1 of System Design Fundamentals.
A great source for this.
And our mission today is to demystify that journey of scaling an app from like a single user to millions of users globally.
And it's a journey of constant crisis management, which is what I love about this.
Exactly. It's not a static blueprint.
No. You don't architect for Google scale on day one. You'd run out of money. You build for what you need now, and then things break.
And you fix them.
You fix them, you change the architecture, and then you grow again, and something else breaks. It's just a cycle.
So let's start where every tech giant started, the garage phase. The source calls it the single server setup.
Right.
Walk us through what that actually looks like.
It's simplicity itself. Just imagine one physical computer, a single box. Everything you need lives right there. Your web server, your application code, your database.
Huh.
It's all roommates in a studio apartment.
Cozy. So when a user types in, mysite.com, what's the actual flow?
It's a straight line. The user enters the domain, the DNS looks up that name and gives back the IP address of that one computer.
And then the browser just sends a request there.
Shoots an HTTP request right to that IP. Your server processes it, queries its own local database, builds a response.
Which is usually HTML for a website or JSON for a mobile app.
Exactly. JSON's way lighter, which is better for mobile. But in this stage, the bottleneck is pretty obvious. It's just physics.
You run out of room.
You run out of everything.
Yeah.
CPU, RAM, disk speed.
Yeah.
1,000 users, and that box starts to sweat.
And 10,000.
It catches fire.
So the first instinct, and this feels very human, is just to buy a better tool. The source calls this vertical scaling.
Or scaling up. It's the throw money at the problem phase.
To just get a bigger server, more RAM, faster CPU.
Yeah, and it's appealing because you don't have to change your code. You just move your software to a bigger machine.
The source mentions Stack Overflow did this for a long time.
Oh, yeah, that's a legendary case study.
Yeah.
Back in 2013, they had like 10 million monthly visitors running on one massive SQL server. So it's possible.
But there's a ceiling.
A hard ceiling. You can't add unlimited RAM to a computer. And the bigger problem, the one the analysis in the text really highlights, is the risk.
The lack of failover.
None. If that one monster server crashes, power supply
Yeah.
blows, whatever, your entire business is just gone. You're offline.
Okay, so we have to stop trying to build a bigger Hulk and instead build an army. This is the shift to horizontal scaling.
Scaling out. Instead of one supercomputer, you buy 10 or 100 average computers.
But that creates a huge problem right away. If I have 50 servers, how does my browser know which one to talk to?
It can't. And that's where the load balancer comes in. This is probably the most critical piece of infrastructure for scaling out.
The traffic cop.
It's the traffic cop, exactly. And it changes the whole setup. Users don't connect to your servers anymore. They connect to the load balancer's public IP.
And then the load balancer forwards the request to one of the servers behind the scenes.
Right, to one of their private IPs.
So they're hidden from the internet.
Correct.
Yeah.
Which is a huge security win. But the main benefit is availability. If server number 5 crashes, the load balancer just notices and sends the next user to server 6.
The user has no idea.
The user never sees an error.
So the web tier is solved. We can add 1,000 servers. But we've just kicked the can down the road, right? All those servers are still hitting the same database.
And that's where things get sticky. The web tier is easy to scale because it's stateless logic. The data tier is hard because it holds the state. It has the data.
You can't just spin up an empty database.
Exactly. It needs the data. So the strategy here is database replication.
The master-slave architecture, I've heard the term, but what's the logic behind splitting the roles?
It's based on how we use apps. Think about something like Instagram. What are you doing 95% of the time?
Scrolling, just reading stuff.
Exactly. You're reading data. You very rarely write data, like posting a photo. So most apps have this huge imbalance, high reads, low writes.
So the architecture mirrors that. You have one master database that handles all the writes.
Yes. Anything that modifies data, insert, delete, update goes to the master. That data is then copied over to the slaves.
And the slaves only handle the reads. So you have one master and like 20 slaves.
Precisely. Traffic spikes. Just add more slaves to handle all the people scrolling.
I see a potential issue, though. Synchronization. If I update my profile photo on the master, then I refresh the page, and my request hits a slave. What if this slave doesn't have the new photo yet?
You've just hit on the classic problem, replication lag. In the real world, there can be a few milliseconds or even seconds of delay. You might see your old photo for a moment.
Which is confusing.
It is. But the bigger risk, the one the text mentions, is what happens if the master itself dies.
The head of the snake is gone. No one can write anything.
Right. You have to promote a slave to be the new master. And that process is not always clean. If that slave wasn't perfectly up to date, you might lose data.
So you need some serious automation to handle that failover.
Absolutely.
Okay, so we've got resilience, but let's talk speed. We're still hitting a database for every page load. That's slow.
It involves disk I/O. We need to stop doing that so much. We need a short-term memory.
We need a cache.
We need a cache.
The source describes a read-through caching strategy. Can you walk me through a request with a cache?
Sure. So you want to load a product page. The web server gets that request. Before it even thinks about the database, it checks the cache, something like Redis, which lives in RAM.
And RAM is way faster than a hard drive.
Orders of magnitude faster. So it asks, do I have the data for this product? If it does, that's a cache hit.
And it sends it back instantly. Database never gets bothered.
Exactly. If it's a cache miss, meaning the data isn't there, then the server goes to the database, gets the data, saves it to the cache for next time, and sends it to you.
Seems like a no-brainer. But the text warns about some pitfalls, like keeping data too long.
Yeah, the stale data problem. If you cache a price for 24 hours and then change it in the database, people will see the wrong price all day.
So you need an expiration policy. It's a balancing act.
It's a total balancing act. Too short, you hit the DB too often. Too long, the data's wrong. And you also have to manage memory.
What happens when it's full?
You have to evict something. The text highlights LRU least recently used as the standard. Basically, kick out the oldest, least popular data to make room for the new stuff.
Okay, that handles data from the database. But what about the big files? Images, CSS, JavaScript. If my server is in Virginia and my user is in Tokyo.
The speed of light is a real bottleneck. It is. That latency is unavoidable if you serve everything from one place.
Which is where a CDN comes in, a content delivery network.
This is essentially geographic caching. You have servers all over the globe. The user in Tokyo doesn't fetch logo.pne from Virginia. They get it from the CDN node in Tokyo.
So it's faster, and it takes a ton of load off your main servers.
A huge amount.
There was a really practical tip in the source about CDNs that I loved, about updating files.
The versioning trick.
Yeah, because if you change your logo but keep the same file name, the CDN might just serve the old one for days.
It will. Invalidating a CDN cache is slow and expensive. So the trick is versioning. In your code, you don't ask for logo.png, you ask for logo.png.v2.
And the CDN sees that question mark and thinks it's a totally new file.
A totally new file. It fetches the new version immediately. It's a simple hack that solves a massive problem.
Okay, so we've optimized a lot. But the source brings up a major architectural shift we have to make, moving from stateful to stateless.
This is the aha moment. This is the key to, truly infinite scaling.
So explain the stateful problem first. What was wrong with the old way?
Well, in the old days, when you logged in, the specific server you talked to, let's call it server A, would remember you. It stored your session in its local memory.
Which creates sticky sessions.
Right. The load balancer has to keep sending you back to server A if server A crashes.
Your session is gone, you're logged out, your shopping cart is empty.
It's all gone. And you can't just turn servers off to save money if they're holding unique user data.
It makes auto-scaling impossible.
Totally. The solution is stateless architecture. We make the web servers dumb. They have no memory.
So where does the session data go?
Into a shared persistent storage, like a central Redis cluster or a NoSQL database.
So now, any server A, B, or Z can handle my request because they all look up my session in that central store.
Yes. The web servers become interchangeable widgets. This is what allows for true auto-scaling. You could just write a script that says, if CPU hits 70%, launch 50 new servers.
And they can start working immediately.
Instantly. That's the secret sauce for surviving Black Friday.
Okay, but what about tasks that just take time? The source uses a photo processing example to introduce message queues.
This is all about decoupling. Imagine your app lets a user upload a photo, and you need to crop it, sharpen it, create a thumbnail. That's heavy work.
And if the web server does that while I'm waiting, the page just hangs.
You're blocking the thread. If 1,000 people do that at once, your whole site grinds to a halt. So you use a message queue. It's a buffer.
How does the flow change?
The web server just takes the photo and drops a message in the queue. It basically says, job 500, resize this. Then it immediately tells the user, got it, we're processing. The connection closes. The user is happy.
And behind the scenes.
You have a separate fleet of servers called workers that are just pulling jobs from that queue. They do the heavy lifting and save the result.
The genius here is that you can scale them independently.
Exactly. If the queue gets long, you just add more worker servers.
Yeah.
It doesn't slow down the main website at all. You've isolated the heavy work.
Okay. We're getting close to the end of the journey. We're global, we have multiple data centers, GeoDNS, caches, queues. But the text introduces a final boss.
Database sharding.
And the text is really cautious about this. It feels like a break glass in case of emergency tool. Why is it so scary?
Because it breaks the fundamental rules of a relational database. Sharding means you split your one giant database into multiple smaller ones.
Like splitting a phone book into A through M and N through Z?
That's a great analogy. You use a sharding key to decide where each piece of data goes.
Sounds logical for managing size. What's the catch?
Oh, the complexity is just massive. First, you can't do joins across shards anymore. The database engine can't see across that gap. You have to write code to stitch that data together yourself.
Which is slow and error-prone.
Very. And then there's the celebrity problem, which I think is fascinating.
It's the hotspot key.
It's a nightmare. Let's say you shard by user ID, and Katy Perry, Justin Bieber, and Lady Gaga all happen to land on shard number 4.
And they all post something at the same time.
Suddenly, shard 4 is getting hammered with millions of requests, while shards 1, 2, and 3 are sitting there doing nothing.
Yeah.
You've just created a concentrated point of failure.
And fixing that requires resharding.
Which is the other nightmare. Moving terabytes of data between servers while the site is live.
Yeah.
It's like open heart surgery.
So the advice is pretty clear. Don't shard until you absolutely have no other choice.
Exhaust every other option first. Cache more, add more read slaves, buy a bigger machine. Only do it when you are literally at the scale of a Facebook or a Google.
That's a very sobering reality check. Complexity is the enemy.
Always.
So we've gone from a single box to a global sharded empire. If someone listening is sketching out an architecture tomorrow, what's the cheat sheet from this chapter?
Okay, the survival checklist. 1, keep the web tier stateless. No session data on the server.
Right.
2, build redundancy at every layer. If something fails, a backup has to take over instantly. 3, cache aggressively. The fastest query is the one you never make. 4, offload static assets to a CDN. Don't waste your server's breath on JPEGs. And 5, use message queues for anything that takes time.
And one final thing that was mentioned, monitoring.
Oh, absolutely. You can't fix what you can't see. At this scale, you need logging, metrics, automation. You have to know a hard drive is failing before your users do.
It's incredible to think this is just the fundamentals.
That's the thing. Scaling is iterative. These techniques get you to 1 million users, but the journey never really ends. You just get more granular. You start splitting up services. But this blueprint, this is how the giants were built.
It makes you appreciate that loading spinner a little more. Or maybe appreciate when you don't see it.
Absolutely.
Well, that wraps our deep dive into scaling from 0 to millions. Here's a thought to leave you with. We spent this whole time talking about architecting systems for human behavior, optimizing for reads because humans read more than they write.
Right.
But as we move into a world where AI agents are browsing the web bots that can read and write thousands of times a second, how does this architecture break? Does read-heavy optimization even apply anymore?
That is a terrifying and excellent question. The caching strategies we just talked about might be completely useless against that kind of traffic pattern.
Yeah.
Might have to reinvent the whole stack.
Something to chew on. Thanks for listening, and we'll see you in the next deep dive.